so the plan is that today I'm going to give a brief overview of the problem, the history, the results, and maybe a little bit of a discussion of the ideas in the proof. And I'll be giving 3 more lectures next week on Monday, Tuesday, Wednesday, and I'll get into more details of the proof kind of techniques in both problems. Okay, so maybe let me start by introducing like the context of these questions, and maybe the scope of what we mean by Hilbert-6 problem in these lectures. Okay, so yeah, so we start with this very broad description that Hilbert had had given in his lecture in 1900, which had this title of this title called mathematical treatment of the axioms of physics. Of course, this, if you just read these words, this is extremely broad title. Like if you interpret it suitably, it basically includes everything like you can imagine modern mathematical physics. And of course, modern mathematical physics has grown into an extent that Hilbert could never have imagined at the time he raised his problem. So so certainly we're not going discussing anything in that generality. So on the other hand, following his lecture in the 1900s, Hilbert actually wrote kind of more detailed article on the precise scope of these problems he raised, and he actually described 2 specific problems. I mean, as the essentially the kind of the particular problem that he had in mind at that time. And the first problem was concerning the mathematical foundation of the theory of probability, which had been solved, we know, kind of in the next like 34 years, 1930s, 40s. And this other problem that he was proposing in his paper was concerning this kinetic theory, which was developed kind of in the 1860s to 70s, kind of a few decades before Hilbert's proposal. Okay, so if we quote his original words, he was talking about Boltzmann's work on the principle of mechanics, suggests a problem of developing mathematically the limiting process, and the limiting process here referred to the discussion in Boltzmann, leading to the going from the microscopic picture to the Boltzmann equation, and which lead from the atomistic view, which concerning these interacting particles, to the laws of motion of continuum, which we could understand as the equation for fluids. Okay, so this is the big picture. Like we'll refer to it as a kind of like Hilbert's program on this connection between the microscopic and the macroscopic. And then there has been a lot of works, a lot of progress concerning this big picture in the 20th century. And we'll just briefly describe like the idea, the way people understand it. So one of the canonical ways to understand it is that there is a two-step process. Like the first step, we go from the microscopic interacting particle system. So there is a microscopic, and there is a Newton collision, and there is we go to this mesoscopic, and we have this Boltzmann, and we go to this macroscopic, and we have these fluid equations. Okay, of course, let me emphasize that this is not unique way to interpret this big picture. So there are also this question of how whether or not you can directly go from here to here, especially in some different scaling laws I'll talk about. But this is a completely kind of different story, and I'll not mention too much, not discuss too much like this line. So we'll take this approach where we start from the the interacting particle system. So this is the objects are particles. The law of law of motion is Newton and collisions. Here the question we're interested in is these density functions, and here we have this velocity field. Okay, so take this approach. We take this from here to here to here. So this is called the kinetic limit. This is the hydrodynamic. Okay. So again, in this series talks, we'll like for let's say 80% of talk will be focusing on the first limit, and we'll talk about in the end we'll talk about the connection, how to connect this first limit to a second limit to complete this full picture. Okay, so this is the plan. So the kind of this in this first limit, the kind of the goal is you go from this in this Newton this system particles centered on Newton's law and collisions to this Boltzmann-Scaling equation. So this is a picture of the representing the kinetic limit. So it starts with a box. So you don't need to have a box. Like you can consider there is a unit box here, a kind of periodic box, or you can consider the case where you have particles distributed in the whole space, but they have a density function that is decays at infinity. So basically, you're considering essentially a finite volume. And we think the size of this finite volume is 1. So we fix this unit scale here. Okay, so consider n particles. So there is this box, unit size. Okay, so there are these n particles. So particles, of course, go to infinity, but on the other hand, their size are going to 0. Size is n particles. Size epsilon. And of course, there is a scaling relation between the number of n and the size of particles, which we call epsilon. And this scaling relation is written here, called Boltzmann-Grad scaling. So I'll explain it in a minute. But basically, we think of the motion of these particles. So usually, they just go in straight lines if they don't interact with other particles. And then if they do interact with other particles, so there is different possibilities of setting up the interactions. So in general, you can think of a potential V, let's say, x minus y over epsilon, which basically means that if the two particles get close with their distance being O epsilon, then they start interacting, which changes their velocities. Okay, so here in this talk, we're going to take the mathematically simplest case, which is called just called the half-sphere model, where you only have these elastic collisions, which means if you have two particles, they have size epsilon, they exactly touch each other. Okay, so the distance is equal to diameter. So we assume in this half-sphere model, we assume that that only in this case do they interact, and in this case they have this elastic collision. So we have this V1, V2, V1 prime, V2 prime, and these V1 prime and V2 prime are given explicit function of these input velocities V1, V2, which we'll show in the next slide. Okay, so this is the picture. We have these many particles. And there is this size epsilon. They interact via these elastic collisions. Okay, and let me explain this Boltzmann-Grad scaling relation. So there is this notion of mean free path. This mean free path is basically the time, so the length a particle travels before the first collision. The average, so this represents average, so average length that the particle travels before it has a first collision. So the idea is that if you think a particle which has size epsilon, and then it travels certain lengths called size L, epsilon, and this is L. Okay, and if you think this particle occupies a volume in the space of which is L times epsilon square. Okay, so we're in 3 dimensions. And then if you think the total number of particles is n, and this number of particles is in a unit volume set, and then if you have this particular volume of this region, then the number of particles or expected number of particles would be n times L times epsilon square. Okay, which you write it L times n epsilon square. Okay, so basically what happens here is that if you choose L, if you call this equals alpha, n times epsilon square equals alpha, and you think L equals 1 over alpha, then essentially this expected number of particles is 1, which means that there is exactly 1 particle on average inside this region that is going to collide with this particle we call X. Okay, so in other words, if you think this this mean free path is the average length of particle travels before its first collision, which is this L. Then essentially alpha is this one word. Okay. So this, if we in this so-called boson-Grad scaling, we're going to set this alpha to be essentially 1, or kind of close to 1, kind of it allows to grow a little bit, as we shall see in our theorem. But essentially, we think this is kind of almost 1, kind of effectively bounded. Okay, so this corresponds to the case of so-called dilute gas. Basically, if you think you have particles of size epsilon, they are fitting in the unit box. So in principle, you can fit in epsilon minus 3 with the highest, with everything packed together. But now you have much fewer particles. You only have, if alpha is 1, alpha is constant, then n equals epsilon minus 2. Okay, so you only have this epsilon minus 2 particle, which means you have your particles, occupy a pretty, small portion of the space, which means you're in the low density setting. Basically, think of the kind of the outer part of the atmosphere, and it's something, basically something close to the boson. Okay, so let me say that this boson-Grad, so it's essentially known that as the kind of essentially the only kind of scaling law, only scaling setup where you do see the evolution of Boltzmann equation. Of course, they are in a denser case, higher density case, say you have epsilon minus 3. You can expect to go directly from the the particle system to fluids directly, but that is a much harder problem mathematically. And again, we're not going to talk about that. So there is one result due to Verdun, Euler, Verdun, and Yao, which assumes there is some randomness each time of collision. But other than that, so there is not many mathematical results in that study, and I'm not going to talk about that study. Okay, so this is a picture. Let us restrict ourselves to this boson-Grad scaling, and now we have this system of particles, this rule of collision, and then we can. So this is a formula for the collision, just to show you. So this is a pretty elementary formula. Basically, the the VI, the velocity with pre means the pre-collisional velocities, and the velocity with post means post-collisional velocities, and they're related by this simple formula, essentially, where omega is a direction vector of the connection of the two centers of the particle. Basically, think of they are round spheres. They are round spheres. Okay, so this geometric setting basically means that if you have particles that are colliding kind of directly in this direction, then their velocity from this formula, their velocity just get exchanged. If you have a v1, v2, then it's going to go back at v2, and it's going to go back at v1. On the other hand, if you have these so-called grazing collisions, then we have basically this kind of setting where the relative velocity is orthogonal to this omega, then they just go kind of in straight line without changing their velocity. Okay, so this is the rule of elastic collision. Okay, and let me just mention that with a few technical manipulations, for example, you need to exclude the case where 3 particles are together, but other than that, it's a well-defined, time reversible and volume preserving dynamical system. And we're starting with this system of n particles, and we're going to see the Boltzmann equation by considering these statistical quantities of the distribution. Okay, so this is the picture. As I just said, so we're taking the statistical point of view of this problem, which means we're studying these S particle density functions. You think there is there's a, let's say S equals 1, there's a 1 particle density function, which is a function of T, Z means X and V. So 1 particle. So F equals F, T, X and V, and X and V, we're calling it to be Z. Okay, so basically this means that the probability density of finding a particle in position X and that velocity V, if we measure at time t. Okay, so this is this 1 particle density function, and then consider kind of multiple particle density function. You have S particles, then basically we have this basically the probability density that you can find You can find your at time t. You can find your first particle at the position x1 in velocity v1, and second particle at position x2 in velocity v2, and last particle at position xs and velocity vs. Okay, of course, it's a question whether or not these different particles are independent of each other, and this is a big problem. Actually, we'll see, which is related to this notion of molecular chaos. But for now, let's just think we have this one particle density, and we have this general kind of S particle density functions. Okay, and then the question is how do we evolve in time? So assume we have this initial density function. Think of the initially these particles are distributed according to a particular law, which give you these variables, the one particle and particle density functions. The question is how does this evolve, for positive time, and how does these densities behave, in the kinetic limit where n goes to infinity and epsilon goes 0, according to this boson gradient. Okay. This is a question we're interested in, and let me just make one more assumption that we assumed initially that these particles, so initially at time t equals 0, the states of these particles are independent. Okay, so in fact there is a restriction that the distance between the xi and xj for different particles should be bigger than epsilon, but this is a minor thing, we're going to ignore that. Essentially, we assume that the initial particles are independent. If they're independent, that means these S particle density functions at time 0 would be a tensor product of these one particle density functions, and we said these one particle density functions is this f0 x2, which will be the initial data for the boson equation. Okay, and the question is how to describe the evolution of these density functions in the kinetic limit. Okay. So at time 0, we have this independence, and hence we have factorization. So the question is whether or not we still expect the same thing at positive time. And this is physically kind of intuitive. So maybe I'll explain the physical intuition in the next lecture. But today will be in shorter time. But basically, there is a physical intuition tells you that these independence should somehow be preserved, up to the low order terms in the limits. However, mathematically, this is a highly non-trivial thing to justify that, and it's referred to as propagationial chaos for these particles. Let me just write it down. This f0, v1, dx, let me call z equals x and v. And this approximate sign, in what sense it is true, is something that is very important. Okay. So for now, for time being, let's assume that this is true. This is true because in early physical literature, people have been just saying, assuming this is true, then they're going to derive an effective equation for the evolution of this one particle density. This one particle density. Okay, and there is a physical, intuitive argument that tells you if you assume this propagationial chaos thing is true, then your one particle density is going to evolve under this particular equation called the boson equation. So I will not have time to explain in detail, but just idea basically how you get these type of things. So this is a linear transport equation. Imagine right hand side is 0, then you just have linear transport, which corresponds to a case where there is no collision at all. So every particle just goes linearly, and of course, if you go linearly, then your density function is going to get linearly transported. On the other hand, there is a collision, and this alpha is a collision rate. So basically, you can think of it as is an inverse of the mean free path, which means that essentially the number of collisions you see in each unit distance. Fine, but what is this QF? This QF is basically that. Okay, so there is this v is the velocity, and v1. So v and v2 are the velocities. Basically, think of this. So there is two particles. So there is this. Okay, so there is this. Actually, this is v, and this v2, and this v1, this v3. Okay, so v and v2 are kind of the two kind of outgoing velocities, let's say. So because you see, you want to look at the density function, which means you want to look at the number of particles at this particular velocity v. Okay, so let's say how can a particle get to a velocity v? That means it collides with another particle. So this particle 1, So now particle 1 collides with particle 2, and then particle 1 becomes velocity. Okay, so this is what it says by this picture. Okay, so particle 1, collides. So this is V3, yeah, V3. Okay. So particle 1 collides with particle 2, and then produce a velocity v. So let's say their initial velocities are v1 and v3, and the other output velocities is v, and the other one is v2. Okay, fine. So then basically what happens here is that first of all, the collision, due to collision rule, we have this mass conservation, sorry, the momentum conservation and energy conservation that corresponds to these two delta functions. So v plus v2 equals v1 plus v3, the momentum conservation, and then the v square plus v2 square equals v1 square plus v3 square, the energy conservation. Okay, and then you think the kind of if you produce a particle at velocity v, then you have to start with particle at velocity v1 and particle at velocity v3. And if you assume this propagation chaos that the states of these two particles are independent, then you really get a density function, the product of the one particle density functions at v1 and at v3. And then that way you get this. So f1, f3, which means f at v1 and f at v3. Okay. And this is so-called the gain term, like in the Boltzmann integral. And there is also this loss term, which corresponds to opposite thing. We'll have a v here, and v2 they collide, okay, and they move out at some outgoing velocity that is no longer v. Okay, so there is this the extra number of particles that comes in, the number of particles that goes away, and this gives you the balance to the Boltzmann equation. So by the way, so if you're working on Boltzmann equation, you may not recognize this term, but in 3 dimensions you can calculate this is by working on delta functions. This is exactly the thing you are more familiar with. Is basically the integral delta of v minus v1 plus v2 minus v3. This is exactly, in 3 dimensions, this is exactly just, so basically v minus v prime times plus, and then you have s r3 times s2, you have this dv prime d omega. Okay, so I'm writing this way because this is more consistent with the wave mechanics picture I'm going to talk about in the second part. Okay, so this is a Boltzmann equation, and now let's review what we have got. We have this this unit box that contains all the particles. There are n particles, each particle size epsilon, and there we have this Boltzmann grad scaling law, and we have interactions by elastic collisions in the hard sphere model, and we have this evolution of densities, and we assume the propagation chaos. Then we get to this Boltzmann equation for the one particle densities. Okay, so now the question is clear. How do we justify all of this? Essentially, the main thing is just how to justify the propagation chaos, and after that, we know how to justify, the evolution, this evolution equation. Okay, so maybe a little bit of history. So this problem certainly has a long history, since the work of Boltzmann, even earlier Maxwell, which who wrote down this Boltzmann equation. Basically, in the early time, people were assuming, physicists were assuming, you have this propagation chaos, and then you can derive this equation by essentially the same argument I described earlier. And of course, there is a lot of debate, how can you assume this? And in particular, the question is, how do you get this Boltzmann equation, which is irreversible? I'll get to that. But okay, so this is the early physical picture. And then it was in 1940s, 50s, where people started to look at this problem from mathematical point of view. So I will cite this this work of Grad, which first realized its importance of the Boltzmann grad scaling, and also posed this as a precise mathematical formulation, and also introduced this idea of BG hierarchy, to this half sphere system, which led to the first set of big breakthroughs in this subject. And this set of big breakthroughs, started with the work of Lanford and also King in 1975, where they were able to rigorously justify this Boltzmann limit, starting from starting from the particle systems in the so-called short time regime. So let me say that there are two parameters. Basically, the alpha. Remember, alpha is a collision rate. So this and basically they were assuming this alpha is size 1, and then time is sufficiently smooth. So there is something important about this, about the short time assumption, which we'll get to in the lectures on next week. But let me just say here, there is a fundamental difference between the short time case and the long time case. Basically, whether in the short time case, imagine you are like only 1% of your particles has one collision and the others have no collision at all. While in the long time setting, every one of your particles is expected to have kind of 500 collisions. Okay, so this is a difference between these regimes. And then subsequently, this work of Ilona Poverenti, which extended results a long time, but in the case where alpha is much smaller than 1. So this has to be in the whole space using dispersive effect of the boson equation. And then in the last 10 years, there have been a large amount of works due to these people, Bodino, Gallagher, St. Raymond, Texier, Séminaire, and many others, where they first of all, they improve Lanford's original result in short time, and they obtain the various linear models on linearized boson equation, and also derive these fluctuation equations, which kind of can be viewed as a second order perturbation to this kinetic limit. Okay, so I don't have time to explain every one of them, but these are kind of basically the most important works on this subject in recent years. Okay, so here's a question. So everything here we have been discussing so far are restricted to either the short time setting or other kind of perturbative settings. Remember, when alpha is much smaller than 1, this is the kind of case where you have every particle barely has any collisions, and even alpha equals 1. If your time is much smaller than 1, then again every particle is barely having enough time to have any collisions. Okay. On the other hand, in order to complete Hilbert's original program, that means we need to match. Remember this kinetic limit and this hydrodynamic limit. In order to match this hydrodynamic limit, because we know in the hydrodynamic limit, we are typically taking a limit where alpha goes infinity, this collision rate goes infinity, so that basically you are reaching equilibrium, which is you're reaching equilibrium of boson equation, which is Maxwellian, and then you can see these velocity fields and so on. So in order to match with this limit, you really need to take in the first limit that alpha is very large, and T is at least 1 or kind of also very large. Okay, and this is a real question that there has been no progress in the last decades on this problem. That how do we get to this derive this boson equation for arbitrary long times? And this question is posed here: can we derive the equation for arbitrary long time? Of course, as long as a solution to the boson equation exists. And this is a thing we are going to talk about in our main theorem and in the lectures in the next week. Okay, so far we have been discussing the particle picture. So there are these epsilon particles. They are interacting with each other by collisions, and they have these statistical quantities given by density function, and we have the boson equation and so on. So the other side of the coin is the wave picture. So since the 20th century, we have been seeing this duality between particle and waves, and it was kind of in the 20s, 30s, where people started to ask the same question, same question in statistical physics, but for the systems of interacting waves. Okay, so there are these studies leading to the so-called quantum Boltzmann equation. There are also the studies leading to the so-called wave-Kinetic equation. I'm not going to talk about the physical picture, but basically just think that there are kind of systems describing interacting waves. So we'll see, for example, a typical example is nonlinear cubic Schrödinger equation. And then you can do the same. You can ask the same question. You can have the same set. You have a lot of wave modes interacting, and how to describe the evolution of the statistical quantities, and what is the kinetic equation that you get. Okay, and this we can call it, I mean, informally call it kind of the analog of this Hilbert 6 problem for waves, although there is lacking hydrodynamic limit because the behavioral wave equation is much different. So we will not talk about it. Okay, so this is starting with the work of Nordheim, Pels, Olin, and Ulenbeck in the 1920s or 30s. And let me mention there are these fundamental contributions made by Hasselmann and Zakharov. So Hasselmann is the one who applied this whole theory to water waves, and in practice they're using it to predict the level of the motion of the ocean surfaces. And Zakharov was the one who discovered this Zakharov spectrum, which had a lot of implications in connection with turbulence and also in connection with this energy cascade phenomenon, in dispersal equations. Okay, so, and these are kind of the scientific kind of aspects. So there has been this weather for ocean wave forecasting models, and has been models applied to the Poisson physics and so on. So since it's a math talk, I'll not get too much into that, but I guess it's good to show some pictures. Okay, so the setup of the problem. So we start with, now we no longer have particles, we think of interacting waves, and this is a picture of interacting waves. So think of there is this, this K and K2 and K1 and K3. Okay, so you can think of it as, like actually what happens is that, okay, so we'll see in the cubic Schrodinger equation like this, but K2 comes with a conjugate. So we are drawing this in this way just to be, for example, these energy conservations are exactly the same as in the particle picture. Think of these as a 4 waves. Okay, so now particles are replaced by waves. Actually, in the homogeneous setting, these waves are just Fourier modes, and their intensity is the same everywhere. In the inhomogeneous setting, you're having wave package, which is slightly more complicated as it depends on the space. But in any case, we have these interacting waves. And then think of you have a large box of size L. So we have this size L, and you think of the Fourier, and then you're going to get this mesh. Okay, so if you think of overall frequency is 1, but then the size of this mesh is going to be 1 over L. Okay, so you have many wave modes, fitting into this frequency range. Okay, and the number of wave modes is L to 3. So number of degree of freedom, L to 3. So this is slightly different from this Boltzmann picture, in that we're having this higher density thing. So the degree of freedom is L3 instead of L2. So in this way, this wave turbulence setting is usually called the weak coupling limit, while the Boltzmann setting is called the low density limit. But there is kind of correspondence between these two cases. So basically, you can still talk about this question. So there are these number of waves interacting, and they are interacting via particular nonlinear potential, which we call the strength is denoted by alpha. And we're considering this cubic Schrodinger equation. So basically, so it's a canonical kind of the simplest kind of canonical dispersive equation. I mean, it actually has a direct analog analogy with a Haas-Sphere model, which will see that the equations they derive is essentially the same except for the nonlinearity. Okay, so this is the cubic nonlinear Schrodinger equation with this alpha. Remember, this alpha represents kind of the strength of the interaction, and then in this large box, between 0 and L. Okay, so in the limit again, we have this alpha goes 0 and L goes infinity. So I said we'll be dealing with homogeneous cases. So in the inhomogeneous cases, so there is this dependence on X. So you still have a transport equation in your Candy equation, and you have the exact analog to Boltzmann. Like in the homogeneous case, there's no transport term, so it's more closer to the homogeneous version of Boltzmann. You only have the dt instead of dt plus b dot dx, but otherwise everything else is still the same. And finally, because we're in a homogeneous version, there turns out to be more kind of flexibility in the in the scaling relation, we can allow these parameters to scale kind of with the arbitrary kind of gamma power for gamma between 0 and 1. Okay, so now this is a setting for the wave kinetic problem, where you start from number of interacting waves represented by the cubic Schrodinger equation. So they are acting on this large box L, which gives you this large number of interacting modes, and then their interaction is given by the cubic Schrodinger equation, and then I have to say the initial kind of distribution, and the initial distribution is again given by this molecular chaos assumption here. Since the objects, the particles are the Fourier modes, we basically assume that Fourier modes are independent of each other. So basically think of this. So there is this Fourier mode, which is this profile. So this positive profile function and times IID Gaussian. Okay, so here this eta k IID, it doesn't have to be Gaussian, but let's assume this Gaussian for simplicity. Okay, so we have these initial modes, which are independent. Again, the question is, these modes will no longer stay independent and as the time evolves, and the question is whether they are still staying independent to the top order. And again, this is referred to as a propagation chaos. Okay, so one more point. This in the particle setting, we're considering these S particle densities, which are the most natural thing you can think of. Now, in the wave setting, since these U are kind of wave functions and U hat are wave functions, so they do not really represent densities. So the thing that represents densities is the mod U square. So basically, we think so. There is this one particle density. In the wave picture, it corresponds to the 2-point correlation, the second moment, and there is this S particle density. In the wave picture, it corresponds to the 2S point correlation, which is okay. Of course, you can see other correlation, but they will all vanish kind of in the limit. But this is one that has a non-trivial limit. Okay. So then, with this correspondence, we know what kind of statistical quantities we are looking at, which are essentially this. Correspond to one particle density, and this essentially corresponds to the multi-particle density. And if you assume propagation chaos, okay, we're going to see that this is again the tensor product of this. Okay, so there is the kinetic time, which is the same notion corresponds to the particle picture, which corresponds to the notion of mean free paths. Again, we think of a single mode, at frequency k, and think of what is the time that it takes before that this k starts to have a nonlinear interaction with the other modes. Okay, remember there is this alpha factor in front of nonlinearity, which means that this nonlinear effect is you're going to see it at a later time, and this exact later time is this alpha minus 2, which is called the kinetic time. Okay, and so far everything has been in perfect analog in the wave setting and in the particle setting. And again, we expect this propagation chaos. That means this should be a tensor product of this. And if you assume that, of course, the question is, how to analyze this. What is the limit of this? Like it should satisfy a kinetic equation, which you'll see is the wave kinetic equation. So this is the wave kinetic equation. So see, this is n tau this n tau k, which is this second moment, and we're really talking about the limits when limits when L goes to infinity, alpha goes 0. Okay, so this object is going to be the solution to this wave kinetic equation, and you'll see that it's exactly the same kind of integral as we see in the Boltzmann equation, except that this velocity v is going to be replaced by the wave number k. But this is exactly there is for Schrodinger equation the group velocity is equal to a constant multiple the wave number k. So this is exactly the same. And this, of course, the only difference between the wave kinetic and Boltzmann is that here you have a cubic nonlinearity instead of quadratic nonlinearity in the Boltzmann case. Okay, so this is why we're saying this model of cubic Schrodinger equation is kind of the exact analog of the half-sphere picture of the half-sphere problem in the case of Boltzmann. Okay, so this is the wave equation that we're going to expect to see, in the limit from nonlinear Schrodinger equations in this picture. Yeah, so let me mention.
This is the only place where the form of the original NLS sort of comes into play.
Okay, so the dispersion relation comes into here. So if you have dispersion relation omega, you have omega k1, and so on. And this is a cubic equation. If you have a different nonlinearity, have different multiplier, then you're going to see this in before this cross, you're going to see this same weight coming from here. So for example, if you have a few derivatives formally, if you have a few derivatives, like in this nonlinearity, you're going to see basically the square of these derivatives. Like if you have a k to the gamma, then here you're going to have a k to 2 gamma, in this Kant equation.
Would you have chosen the nonlinearity to get exactly the same of in the Boltzmann case?
No, this is a cubic.
But if you make it not cubic?
If you have a quadratic, NLS, then you are going to have a 3 waves. So you're not going to have a 4 waves here. You're going to have 3 waves. So you cannot get exact Boltzmann. Okay, but what you can get is that there is this quantum Boltzmann equation where you can get from this many particle system with linear Schrodinger equation with interaction potentials, that the nonlinearity is a linear combination of the quadratic and cubic. Remember the Boltzmann is have something times n1 and 3 minus n2, and the wave equation will get something times n, basically n1 n3 n plus n2 minus n2 n1 plus n3, and basically the quantum Boltzmann equation is going to really a linear combination of those, which we see is that n1 the same thing times n1 n3 times let's say plus minus 1 plus n2 minus n2 plus minus 1 plus n1 plus n3, which if I memorize correctly, this plus 1 is corresponding case of bosons, and the minus 1 is corresponding case of fermions. Okay, but again, that's a completely different thing that I'm not going to talk about. There is a similarity in the equation, but of course the derivation is still completely open here. Okay, so yeah, so the few remarks on this page. When in the homogeneous things, there are no transport terms, so this thing and this motion. Okay, so here I think the setup of the problem is now clear. We have the root, we have the interactions, the kinetic limit, the initial data, and then the propagation chaos, and then these expected kinetic equations. Again, I have a list of mathematical works starting from Spong in the 1970s, and these I would say seminal works of Erdős Yao and Erdős Semmelhoff and Yao, where they completely solve this problem in the linear setting. And then this work of Lucien and Spong, which started the analysis of a nonlinear problem, and then the Buckmaster, Germain, Hani, and Chatat started the case of off equilibrium settings. And later the work of myself with Hani, and at the same time Colin and Germain, which reaches something really close to kinetic time. And finally, in the previous work of myself with Hani, we have been able to reach exactly this kinetic time again for short time. So this corresponds to Lanford's result. We have this sufficient short time, which allows you to do the expansions. And also, let me mention this work of Stephanie and Chuan, and of which did the same result, but for KdV type equation with stochastic forcing. Okay, so then
kinetic time here depends on the scales that you have in your problem.
Kinetic time is this yeah, so T kinetic is this is alpha minus 2 in the wave kinetic setting, and if you have a kind of a short time, means that this rescale time tau is small. You are reaching a small multiple of the kinetic time. Okay. So I have a few minutes to explain our main theorem. So the first main theorem was, in the timeline, we first worked out this result for the wave kinetic problem. So again, suppose the solution to wave kinetic equation exists for any given time interval. So tau star is not necessarily small. Actually, it can be arbitrarily large if your solution has a global, if your equation has global solutions. Then we have this. So we have this, the second moment is given by the solution to wave equation plus the error term, which explicit goes to 0 at the explicit rate, and when L goes to infinity. And we have all these propagation of chaos, which doesn't fit in one page, but you understand that these are all true in the full interval from 0 to this tau star. Okay, so this is our first theorem. And subsequently, in 2024, we have been extending these results to the Boltzmann equation. We'll go from this particle system to Boltzmann, and again assume the solution to Boltzmann equation exists for on some any finite time interval. Again, this time interval has length going to infinity if you have global solutions. For example, if you are close to the Maxwellian and you do have global solution, then this T star can be made arbitrarily large. Then again, this S power densities is given by the tensor product. So this also proves the propagation of chaos. And then, okay, so you have this this remainder term, which again goes to 0 in the particular polynomial rate in measured in L1. Okay, and again, this holds for the full time interval and as long as solution exists. And finally, so as I said, so there is this thing. We go from particle to Boltzmann, from Boltzmann to fluids. So I didn't mention that, but the parts going from Boltzmann to fluid alone, this has been known due to the work of important work of many people. But essentially, this part is kind of known for most of the models we're considering, like especially when you can just find the limit going to the compressor of Euler and incompressible Navier-Stokes and a bunch of other equations in different settings. The main question, as I explained earlier, is how to connect this limit with this limit, because this limit requires alpha to go to infinity. Now, in our theorem, since we are allowing time to go to infinity, and also I didn't write here, but we do allow alpha also to go to infinity. So then this allows us to match this limit with this limit, so that we can get this kind of the whole thing, starting from the particle system, particle to Boltzmann, and Boltzmann to fluids, and finally derive the fluid equation. So this, in some sense, is completes Hilbert's original program. Of course, in this particular Boltzmann grad limit, which is a limit where we really see this intermediate step of Boltzmann equation. And just a sample of theorem looks like this. If you start with the Hart-Sphere system in the torus, we need torus for some technical reasons, and we need dimension 2 and 3 for some technical reasons, which I'm not going to talk about. With initial data given by this Maxwellian type of thing. And then the idea is that if you consider this Boltzmann equation then in the limit where alpha goes to infinity, you're going to see your solution converges to the same kind of form of Maxwellian with these parameters, this rho, this T, and this U. So rho is the density, T is the temperature, U is the velocity, and these things evolving according to the Euler equation. And if you consider the perturbation of global Maxwellian, you in the second order approximation, you get Navier-Stokes. So okay, but essentially let's just look at the Euler equation, and then in the iterated limit, we'll first let n goes to infinity and let alpha goes to infinity. Then this one particle density is given by this converging to the solution to compressor Euler, to converge the Maxwellian given by the solution to Euler equation. Yes.
And if it's iterated limit, why is it different than just the combination of the two existing results?
It basically is. So yeah, it basically is. I mean, there is some technical things that you have to fit everything in torus. You have to fit everything in 2D and 3D. But essentially, that is a combination of two results. I mean, and also I think there's the next slide. But basically, in next slide, you're allowing to choose alpha. So iterated limit. It's okay. And also, you see next slide that you're also allowed to choose L goes so n goes to infinity, and alpha to be goes to infinity as log n goes to infinity. So if you want, you can take them kind of in this way. But yeah, essentially, this is a combination of two results. Okay, so maybe a remark I just said. So we're allowing to to take this long time to go a little bit to infinity, like as a log. It's a very interesting question whether we can even improve that. This is unknown at this time, and also allow this alpha to grow a little bit. And there are the inhomogeneous cases and so on. I mean, something that we expect to be true, but not necessarily kind of as proof as simple as these. So I don't have time for the ideas, but fortunately I can talk about ideas in the lectures next week. So let's get to this some open problems. So the first page concerns open problems in the setting of wave turbulence. Of course, the biggest problem is the quantum Boltzmann equation, and there has been a lot of recent results, but none of them is really reaching the kind of the core of the question. And also this behavior of the wave equation itself is also a very interesting thing. It's very different from the Boltzmann equation. For example, you're going to see this Zeckel spectrum. You're going to see generic. You're going to see some kind of singularities, and what these would imply for the Schrödinger equation. This again a very interesting question. And more other equation, the quasi equation, and in particular in 1D turbulence. So I didn't say that in our theorem for wave turbulence, everything is in dimension 3 and higher. So we expect the same result to be true in 2 dimensions with a little bit more complicated proof, but 1 dimension there's something pretty much different, like the turbulence, there are these interaction, there are many degeneracies that changes things a lot really. So there are this 1D water wave, MMT, the FPUT model, and the kind of anomalies happening in 1D. And of course, what if the wave equation itself is locally ill-posed? Does it mean anything different? And regarding the Boltzmann picture, so first of all, this question of fluctuation large deviation, we expect this to be maybe relatively easy. Like it's probable to extend these results to the this work of Bodino, Gallagher, Serum, and Bodino, Gallagher, Serum, Séminaire to these long times. But there are kind of much harder question, like can we extend the result to allow for kind of slightly singular solutions? And can we reach longer time scale? I think this is a very fundamental question. So, for example, if you are close to Maxwellian, can we expect to get something slightly better? And of course, there is derivation Leno equation, again, kind of completely open at this time. Okay, so this is just an overview of the whole picture, and I hope to explain kind of more details. So basically, I have 3 lectures. So I think I'll spend kind of 2 of lectures describing the proof in the case of Boltzmann, and 1 lecture in the case of wave turbulence.
Thank you very much.